Hi folks, I'm here to re-record the lecture that was given in class yesterday for the remainder of Example 1 and Lecture 1 in Generalized Linear Models. My little laptop at home wasn't strong enough to do the Zoom and the recording at the same time, so I decided not to record. That way everything could work for the people who had attended class, but as promised, I am re-recording it for those who were not able to be there or who just want to hear it again. So I'm starting on page 11 of Example 1. This is our review of general linear models involving interaction terms. And this is the last part of this example, our final model that describes how to interpret an interaction that involves a categorical or grouping variable. In particular, we have two new interaction slopes needed because we have three different dementia groups, and we are examining how the effects of dementia differ by gender. So in this case, because gender only has one slope differentiating its two groups, and we have two slopes differentiating the three dementia groups, we need two slopes to compute the interaction. So this is a little bit different than the previous model, which we examined age by grip. It only required one interaction because we had only fit linear slopes for age and grip, and therefore their multiplication only required one additional parameter. So to foreshadow what is going to be tested by this interaction term, I have what is known as cell means here inside this little box. And we have the 6 possible means for the 2x3 combination of men and women and the 3 dementia groups. Given the way that we have coded these variables, in gender, men are the reference, and in dementia, the none group is the reference. That means men without dementia are going to be the reference cell. And the main effective group over here, beta 3, is going to tell us how women differ from men, but given the interaction term, beta 3 is how women differ from men only when the interacting predictors are 0, which is for the none group. So beta 3 is going to tell us this 29 versus 26 distinction right here. Likewise, the main effects of dementia group, beta 4 and beta 5, are only the effects of dementia group when the interacting predictors are 0, which is gender. So that means that these are the dementia group differences specifically in men. So beta 4 is going to tell us about the 29 versus the 23, and beta 5 is going to tell us about the 29 versus the 17. The interaction terms then, or differences of differences as they are sometimes called, is going to tell us first for beta 7 how this difference between men and women differs between the difference between men and women in the future group. So this difference is about 3 favoring the men. Likewise, this difference is about 3 favoring the men. So that interaction term is going to be near 0 because the gender difference is basically the same in the none group as in the future group. In contrast, beta 8 is going to tell us how the gender difference changes if you move from none to current, in which it is much bigger. So we would expect that the beta 8 parameter is going to be larger because the gender difference is so much bigger in the current group than in the none group. So the model is only going to give us certain pairs of differences, but we can get all of the pairs of differences that we want as linear combinations. So the logic by which to do so is shown here. So for instance, if I want the gender slope, the procedure to figuring out what the gender slope would be for any value of a moderator is to go into the equation, find all of the terms that involve the slope of interest, which is the gender slope here, bring them down, and then factor out the variable that the slope is for. So when all is said and done, these 3 terms are my ingredients to how I would compute the effective gender at any level of dementia. So beta 3 is what it would be if we're talking about the none group, which is where these 2 terms would drop out. Beta 3 plus beta 7 is how we get to what the sex slope would be in the future group, and beta 3 plus beta 8 is how we get to what the sex slope would be in the current group. So beta 7 and 8 are how the sex slope differs in those alternative dementia groups. They always are going to be differences. Likewise, we have the differences among the dementia groups, specifically in men, and only 2 out of the 3. So to figure out what they would be in women, we do the same process, go into the equation, find all of the terms that have the slope in question, bring them down. So just 2 for the effect of dementia, none versus future. Factor out the variable that the slope is for, and then what's left here are the ingredients for figuring out the dementia group difference for any value of the moderator. The same is true for the other version of the dementia group difference. And then to get the missing third contrast for future versus current, it is whatever it would be for current, which is right here, minus whatever it would be for future. So this combination of 4 pieces is what we would need to get the difference between future versus current. How current differs from future is the way I would say that for any value of the moderator for gender. So we had looked at the code and gone through the patterns here. So here's the R syntax for that. The status syntax is at the end. So note we have the 2 new interaction terms at the end of our list of fixed effects. Let me make this a little bit bigger so we can see it more easily. In terms of interpreting the model coefficients, the intercept interpretation has not changed, so the value of it has changed because the model has changed, but this is still the predicted cognition outcome for an 85-year-old with 9 pounds of grip strength who's a man without dementia. The interaction terms do not change those conditionalities. Previously, we had talked about the effects of age and grip and their interaction. So in this pattern, because age has a negative slope, the positive interaction is going to make the slope of age weaker or less negative as grip strength increases. So for every additional pound of the moderator grip strength, the age slope becomes less negative by 0.12. Likewise, if we start with the grip strength slope, that is positive in the 85-year-olds, and the interaction term will make it more positive as age increases. So the grip strength slope itself will become more positive or stronger per year of age by 0.12. So we spent our time concerned with these terms right here. So we have, combined with the intercept, we have 6 fixed effects. That means we're going to perfectly recreate the pattern of means for our 2x3 combination of gender and dementia group. So first, this is beta 3. This is the gender effect, and given the coding with men as the 0 and women as the 1, that means that the coefficient of negative 2.87 is going to apply to women. So women are significantly lower than men in our cognition outcome if we're talking about the none group, because that's when these interaction terms would drop out. What happens in the alternative groups then is guided by the interaction. So the interaction tells us how the gender effect differs in the 1 group for the dementia contrast, which is future. So in the future group, this negative gender effect that is favoring men is going to become less negative or weaker in the future group. Not significant though, and that matches our patterns that we saw earlier. The gender difference in the future group is basically the same as the gender difference is in the none group. In contrast, if we talk about the gender difference in the current group, we have a different pattern. In this case, the gender difference is larger because it becomes more negative in the current group. So altogether, the gender difference would be the minus 2.8 plus the minus 7.8. So a much bigger gender difference in the current group. And that shift in the gender difference, that increment to the gender difference in the current group, the interaction term is significant in this case. So we have only some of the simple effects of interest. We have everything that is pertaining to a reference group as part of the model fixed effects. So we know what the effects of dementia are in men relative to none. Likewise, we know what the effect of gender is in the none group, and anything that's involving differences among the alternative groups or simple slopes in the alternative groups, we have to ask for as a linear combination of fixed effects. So we talked about that in class as well. So continuing down the output, the next thing that I asked for is an omnibus test of whether we have a significant gender by dementia interaction. Recall that that's 2 different slopes here because there's actually 3 different single degree of freedom interactions that are embedded. So we have to ask for a joint hypothesis test of these 2 slopes against 0 at the same time. The way that this is interpreted is that the comma means don't try to add these together. Leave them as separate slopes, but set them both equal to 0 and tell me how much worse my model gets. So in doing that, the f-test that goes with it, the value of the f is 3.49. The degrees of freedom for the numerator of that test is 2 because that's the number of slopes that we have jointly tested. The denominator degrees of freedom is the number of slopes we could have still added to the model based on our sample size, so that stays the same. And indeed, these two interaction terms are significant. So given the order of the model in which these are the two new terms relative to the previous model, that means that another way that I can interpret this f-test is as the test of how much stronger or better the model R-square got. So this is analogous to what we would call hierarchical regression, in which you can ask for a test of a set of new slopes added as a group to the model. That is exactly what we have just done. Added two slopes as a group to the model because those two slopes conceptually work together to describe the gender by dementia group interaction. Then I asked for what I would call simple dementia group differences within each gender. So this is a combination approach where I am asking for potentially a linear combination of fixed effects to create one slope, and then asking for a joint hypothesis test with a second slope that is also itself a linear combination of the model fixed effects. So the first one is not a linear combination in each, but the second one is. So in these sets of zeros and ones, and recall, these are multipliers to be used for whatever slope has been estimated in its spot. So the first one is actually for the fixed intercept. The rest of these are for the fixed slopes in the order in which they appear in your output. So what I'm referring to here is the dem NF slope, which I know is for men because of my coding scheme, and the dem NC slope, and I want to ask for a joint hypothesis test of those two slopes together. That turns out to be, yes, significant. So in men, there are differences across the three dementia groups. In women, though, in order to get what the two dementia group differences would be, each slope has to be created as a linear combination. So this one is the main effect of dem F, which is in men. This one adds to it the gender by dem NF interaction, and the combination of those two gets me to what the dem NF difference would be in women. Likewise, this is for dem NC and the dem NC interaction with gender. Together, those fixed effects create one slope that tells me the dem N versus C difference. This one is N versus F. And then that one, also significant, looks like it's a stronger effect, just eyeballing these numbers here. As I said in class, at this point, if you're trying to write a results section or give a presentation on these results, your reader or your listener is going to be begging you for a picture. In order to demonstrate or make a visual depiction of what this interaction pattern would imply, we first have to compute predicted outcomes for every combination that we would want to show. So the focus then of this set of predictions is to describe the interaction term of gender by dementia. So we're setting age and grip to 0 this time, controlling for those. And I am asking for using the prediction package to create predicted outcomes for gender 0 or 1, 0, 1 for each of my dementia group differences. And as we had discussed in class, R is perfectly happy to give you combinations that do not exist in your data. So in this table, it tells you what value has been given to the set of predictors here. So for someone with a 0 for gender and a 0 for the dementia group contrasts, this is the predicted outcome for a man in the none group. Likewise, going from a 1 in the gender category but staying at 0s for dementia means this is for a woman without dementia. These two rows, because of NF switching to 1, are going to be men and women in the future group. And then we have men and women in the current group, given these two values switching to 1. The last two rows, which I have highlighted in red as nonsense, are for people who are both in the future and current groups, which cannot happen given our coding scheme. So the first thing that I would need to do is delete these two cases because they would not be part of my picture. So the code here below is a way that I can do that. So I first took this piece of output and converted it into a data frame. I then summed the dummy codes and I said, keep the cases if the sum of the dummy codes is less than 2. So that would involve only these groups and not these ones. I then made a new variable that would be demgroup so that I could use it to make plots, and then I made plots with gender as the x-axis or dementia group as the x-axis. I'm not going to ask you to do this ever in your homework, but it's a useful thing to know how to do, so I wanted to give you some resources to get started on how to make plots. So these are the two plots that we looked at. The one on the left here has dementia group on the x-axis, which is not a continuous variable, so this plot's a little bit weird, but I think it's effective nonetheless. So we have 1 is none, 2 is future, and 3 is current. And this plot shows pretty clearly that there's a much bigger gender gap for the current group than there is for the none group, so that was significant. The none and future groups have the same gender gap, so that was the non-significant interaction term. But the third comparison we haven't seen yet is actually whether the difference for the future group is the same as the difference for the current. And it looks like it should be not the same, but we don't know whether or not that's significant because of the sample sizes in the future and current group are much smaller. So even though this does look like numerically a much bigger gap here than here, we don't know if that gap is differentially significant. We can also talk about gender effects. So the green line shows the gender effect in the current group. This is for the future group, and this is for the none group. So the current group has a bigger gender effect as indicated by the slope of this line or the gap between the lines right here. The fact that all of the lines are negative indicates that current is lower than future or none. So then to get all of the potential pairwise differences, we call those simple effects, even though they're not simple, they're complicated. I have a list here, and I'm listing out all the combinations in one spot so that it's a little bit easier to understand the results. So the first 3 here are the 3 possible gender differences for each group. That means that all that's turned on is the main effect of gender, and then turning on the interaction terms for which dementia group I want the gender effect for. Likewise, there are 6 possible pairwise dementia group differences, 1 for each pair of dementia groups and for men and women. So in this case, what gets turned on is which dementia group we're talking about. So none versus future here, and none versus current here. To get to the missing comparison, we would literally subtract these lines. So if we take the current line here and we subtract the future line, that's where we get the combination of -1 and 1. And then the interaction terms turn on and off if we are talking about men versus women. Then last but not least, there are 3 different interaction effects that are possible here because we have a 2x3 combination. I'm trying to convey the idea that each interaction, so I have an A, B, and a C interaction, each of these can be interpreted in 2 different ways because we have 1 predictor and 1 moderator, and we can switch the role that those play. So for instance, the first interaction effect I've labeled A can either be interpreted as whether the gender gap differs between none and future groups, or whether the none-future effect differs between men and women. Either way, that is given by the first interaction contrast in the model all by itself. Likewise, the second one, whether the gender difference is different between none and current, or whether the none-current difference differs between men and women, is given only by the second interaction contrast. So the point of this exercise is really to get the third one that's missing, which is the comparison of the alternative dementia groups, future and current. And so to be able to do that, it's -1, 1, so that we have current minus future, and the order of the tests matches everything else. So then here are the results of all of those statements, which I broke down and labeled for us. So here are the 3 possible gender differences, much bigger in the current group as we saw. Here are the 6 possible dementia group differences. So there's the dementia group is similarly, I would say, affected in men and women, it looks like, but this one looks like it's much bigger for women, and this one looks like it's much bigger for women. And indeed, these interaction contrasts tell us exactly that. So the 0.16 right here, that is whether the gender difference differs between none and future, or the none-future difference differs between men and women. 0.16 is the difference between this slope of -6 and this slope of -5. Likewise, the gender difference between none and current, or the none-current difference, is this -7.8 is the difference between this slope of -11 and -19. And last but not least, future versus current, the -8 interaction is the difference between this -5 and the -13. So when you're working on these sorts of linear modeling exercises, I find it very helpful to have all of the differences labeled like this so that you can clearly see the direction of the coefficient means that this one is more negative or stronger than that one. In your homework, I worded the direction of the interactions as creating weaker versus stronger effects to help cut down on a little bit of the ambiguity. The last thing that we talked about in class is the somewhat controversial take that some folks have heard that when an interaction is significant, you should not interpret the main effects. The key to understanding the logic behind that statement is appreciating what is meant by main effect in that context. So back to the table here. In traditional ANOVA language, we would call the unique combination of each of the interacting variables a cell, and we would call the aggregate version the margins. So these are marginal means down here, which are averaging over men and women for each of the dementia groups. Likewise, these down here are marginal means for men and women averaging over the dementia groups. And when people say don't interpret a main effect in the presence of a significant interaction, it's these ones they're saying to ignore, and I totally agree. Because this does not tell us what the gender difference would be in any group. It's on average across the groups, which is potentially misleading because there's barely any difference in the gender difference here, but there's a much bigger gender difference here. And so this averages over that and doesn't tell us anything useful. The same is true over here. So these main effects we do not interpret. But if we're talking simple main effects, meaning within the table of the cell means, we absolutely need to interpret these because these tell us what the interaction term is doing. Is it strengthening a difference or is it weakening a difference? The interaction terms and the simple main effects work together to create each of the possible differences. I didn't have output inside this handout for the Stata version of the model, but in the online files that go with this example, I have full syntax and output in SAS, Stata, and R for everything. I will note that the process for fitting the models in Stata is very much the same as the previous model, so we can use test statements to create f-tests for multiple slopes at the same time. So this one is going to give us the test of the omnibus interaction, also the test of the change in R-square from adding these two terms to the model. These test statements give us the effects of dementia across the three groups within each gender. So that's why we have a linear combination within a parenthesis to create the slope of interest, and then a separate linear combination. So it's adding together within the parentheses, but then keeping the results of those separate in terms of creating a gender-specific f-test. Margins can be used to get all possible cell means, and again we have the same problem. Actually, no, I wrote it so that we didn't have that problem in this case because I am creating a separate margin statement for each dementia group and then only going across gender. So this is only going to give us the cell means that we directly need. Then we have the simple slope differences for gender per group. And this is the 1, 0, 1 combination that we saw in the R-GLHT statement, just more explicit because we can see the coefficient that each 1 and 0 is multiplying directly. Here are the 6 possible dementia group differences with the same patterns of zeros, ones, and negative ones as we discussed earlier. And here are the interaction contrasts, where the last one is really the only one we need to ask for to get us the missing interaction related to the future versus current and whether that difference differs across genders. And then here's the code to make the pictures. One thing that I noted in class is that every example that I give is going to have some kind of results section. So all of the words that I said are going to be in this write-up. So this also describes how you would report the results of an F-test. It has a very standard format. So for instance, here's the one for the model. It's F and then degrees of freedom in parentheses, where the first number is numerator degrees of freedom. That's the number of slopes the F is lumping together. Denominator degrees of freedom then is the number of slopes that could have been added still based on your sample size. This is the F-test statistic itself. MSE stands for mean square error, and that is otherwise known as mean square residual or residual variance. That is the amount of variability left over in your outcome. And the reason to provide this number along with the degrees of freedom and the F value is that this is all you need to be able to recreate the rest of the sums of squares table if you so choose. This is the p-value that goes with the F, and then R square is the effect size that goes with the F. This is the proportion of variability that the model has explained with its fixed effects. It is also the square of the correlation between the predicted y hat from the fixed effects and the actual y from the data. So then we have the results section describing how to interpret the slopes and what slopes we're referring to. I don't normally do this when I write results sections, but here I did, where I made sure to put all of the coefficients into the problem. I also showed, for instance, how linear combinations were created by which betas and what the numbers were. Again, that is more for pedagogy than what I would typically do in an article, but if you have a lot of comparisons you're reporting, this can help make it more clear to your reader exactly what you're talking about. And then last but not least, here's an example table where each of the terms then has its corresponding equation term going with it. Notation is important. And that's it. The other thing that I wanted to do very briefly is hit the last couple slides about three-way interactions. Whoop. Come back here. There we go. So three-way interactions sound like a nightmare, but they're actually not that bad if you approach it from the same algorithmic process. That is, simple effects, meaning conditional effects beta 1, 2, and 3 for these three variables right here, they still mean that y goes up or down. It's just that now they're conditional on all of the other variables that they interact with. So this effect of w is specifically for x and z of 0 and so forth. The two-way interactions then also become simple interactions. I know that is a horrible phrase, but that is what it means, because each of these is conditional on the third variable being 0. So for instance, beta 4 describes how x moderates the slope of z, specifically when w is 0, and the others would work the same way. And then the three-way interaction term operates directly on the two-way interaction terms within it. So the three-way interaction takes each of these two-way interactions and makes it more negative, less negative, more positive, or less positive. And it is unconditional because there is no four-way interaction. In chapter 2 of my book, I worked up through a three-way interaction, and I even had a four-way interaction to show how that process would be the same in terms of the underlying algorithms to get the slopes for each variable and for each pair of variables. Here is the math for that. So if I wanted to know what the slope of w is for any value of its moderators, I go in here, find all the terms that have w, factor w out, and the ingredients of what's left is my linear combination. So I would have to know both x and z to figure out what the slope of w is. The same is true for the other variables. And then the new part here is the idea of a simple two-way interaction, because each two-way interaction is going to be moderated by the third variable. So the ingredients to form the conditional two-way interactions for any value of its moderators would be right here. Ta-da! I am calling this one done. Thanks for joining us.